Problem 4.1. So let's start by looking at the two plates. The two plates are 1 millimeter apart and connected to opposite terminals of a 500-volt battery. We can find the electric field between them. If they're two plates, they're relatively close together, the electric field is going to be the change in voltage divided by the distance, so 500,000 newtons per coulomb. Next, to find the polarization, or the dipole moment, let's look at table 4.1. There we can see that the atomic polarizability of hydrogen is 0.667. In the footnote to that table, it says that polarizability is alpha divided by 4 pi epsilon naught in units of 10 to the negative 30th meters cubed, which means we can say that alpha over 4 pi epsilon naught is 0.667 times 10 to the negative 30th meters cubed. Solving for alpha, remembering that epsilon naught is 8.85 times 10 to the negative 12th coulomb squared per newton meter squared. That gives an alpha value of alpha equals 7.417 times 10 to the negative 41st coulomb squared meters per newton. The dipole moment, P, is given by E times alpha. We are doing this in the scalar form, so we are basically ignoring direction. E times alpha gives us a total dipole moment of 3.709 times 10 to the negative 35th coulomb meters. In this scalar form, P is equal to Q times D, so we can solve for D, the distance or the separation between the electron and the proton, by P over Q. P was 3.709 times 10 to the negative 35th coulomb meters. Q is the charge of an electron or a proton, i.e. the elementary charge of 1.6 times 10 to the negative 19th coulombs. And that gives us a total separation distance of 2.318 times 10 to the negative 16th meters. In comparison, the hydrogen atom has a Bohr radius of 1/2 angstrom, which is 5 times 10 to the negative 11th meters, which is approximately 200,000 times this distance. If we assume linearity, it would take approximately 200,000 times this voltage right here in order to ionize the hydrogen.